Go. Okay, now we have 1D collisions. And now, mind you, if watching you guys out in the parking lot, those are almost always a two-dimensional collision because you guys are always at some sort of angle to each other when you run into each other or push other cars out of your parking spot or that sort of thing. So we're going to simplify it right now just for principle's sake, and we've got so we have 1D collision. So quick review. The momentum, which is given by P, equals mass times velocity. Eesh, ugly. Okay, P equals mv. And that our impulse, which is given by J, which equals delta P, equals integral of our net force times our time. All right, so here's our collision. And when we're working through our collisions, when you have a collision problem, I highly recommend that you add to the procedure a before picture and an after picture. What does it look like before they collide? What do they look like after they collide? There are 1D collisions can also be considered as explosion problems because they're just kind of reverses. So explosions are 1D collisions in reverse. So if all the particles are together and then they spread out as an explosion, that's the same thing as all particles out coming together and colliding. Okay, so we want to do it before. Okay, and before we have, you guessed it, a crate. I unfortunately don't have my sedan as a readily available cut and paste thing for this program. I wish I did that because I would much rather use my sedan. All right, so here's our crate. Okay, here is crate 1. Okay, it has mass 1, and it is traveling with a velocity 1. Okay, by the way, this is going to subscript you to death. We are going to have so many subscripts right now that we don't want you to get lost in what's going on, although saying it out loud and writing them at the same time is easy to get them confused, so there's a lot of them. On our first crate, we have a spring. Okay, and our spring, and then this is moving towards, has the initial velocity, towards crate 2 over here. Okay, crate 2 has 0 initial velocity, and it's just standing there. It's just waiting for the collision. Okay, this moves in with a velocity, and then we're going to I'm going to draw you guys the during. You guys don't need to do a during a collision, but we're going to have a during for this one. Now, when they collide, we again have our surface and here is crate 2, and our spring becomes completely compressed during our collision. Okay, and in this moment, during the collision, okay, we have the spring completely compressed. According to Newton's third law, the force of our first cart, okay, on the second is going to equal the force of our second on the first. Yes? So, 2 is going to experience a force in that direction. The force of 1 on 2 is going to go in that direction, as well as 1 is going to experience the force of 2 on 1. Yeah? All right, now, Here's the thing. Check this out. Here's how this happens. When they collide, okay, I still need to zoom out more. I need to get way out here. All right. Not only is this thing moving this way and this one moving this way, but we also have our forces, right? So when they collide, we have that happening, right? So here's one coming in, and they start moving off. Yeah? Now, not only do they collide, but this happens. Okay, so it's sitting here, this one's coming in, time. Yeah? So we have a time that occurs. This happens over a period of time, and then it moves away. Right? Okay, so if this happens over a period of time, okay, not only do we have equal and opposite forces, but we have equal and opposite forces that occur over the same period of time. And delta t. Yeah? All right. So, these forces exert on each other over a period of time. Well, what do we know is force times time? We just defined it. Okay. No, force times distance is our work. Okay, do not confuse these. Force times distance is work. Force times time is our impulse. So, this becomes the change in the momentum of 1 is equal to, oh, I'm sorry, this should be negative over here, is equal to the negative change in momentum of 2. Or plus, oh, poop. Okay. So P1 and P2, okay, if we add them together, they equal 0. Yeah? All right, so there's something to here. Okay, now, mind you, this is, if this is our system right here, there's no external forces acting on this system. Right? It's all internal stuff. It's all gravity working on these guys. The spring is a conservative force within the system. There's no friction. These are guys. Okay, so the entire system has no change in momentum. That's what's going on here. P1 and P2, okay, equal the change in momentum 1 plus the change in momentum 2 equals 0. We saw this earlier. Okay, I think we saw it yesterday. Okay, if our change in momentum equals 0, this must be what? It must be conserved. If the total change within the system equals 0, that constant is conserved. All right, now we're going to start getting subscripty here. So hang with. Delta P1 and delta P2. Okay, we're going to do from this one over here. So delta P1 and delta P2. Delta P1 is going to equal the mass of 1 times the velocity of 1 final minus the mass of 1 times the velocity of 1 initial plus the mass of 2 times the velocity of 2 final minus the mass of 2 times the velocity of 2 initial. That is going to equal 0. Delta P1 is this. Delta P2 is this. You guys cool with those? We did 2 substitutions. We substituted the delta and we substituted the MV for the P. Yeah? Okay. Now what we're going to do is we're going to separate our initials and our finals. So we're going to have the finals on the left and the initials on the right. Subtract both of the initials. Okay, so we're going to have M1 V1 final minus plus, there it was, M2 V2 final equals M1 V1 initial plus M2 V2 initial. Well, what does this wind up being? Okay, this is telling us that the total momentum that we finish with is equal to the total momentum that we start with. PF equals PI. Okay. Now, again, what was the assumption on all of this? Okay, the assumption is that there are no external forces, right? If there was an external force acting upon this system, okay, momentum would not be conserved. If one of them was sliding over a friction over a rough surface, okay, or both of them for that matter, okay, or if there was some part of the collision that was lost due to heat, okay, like when you slap hands, okay, or in other situations in real life, okay, there are other external forces. There's really only a certain couple cases where this is absolutely true and it can be taken as is. Oh no, wait, no, I'm getting ahead of myself. Sorry. What I didn't do for you guys, I didn't draw the after. So let's go over here to black again, and let's extend this so that after, all right, after we have block 1 on its wheels, okay, and it has re-extended its spring, and we have block 2 on its wheels. Okay. Now, before I tell you which way things going, here's how it really works. When things collide, okay, and we'll I hope to do some of this on Friday. When things collide, the heavier mass, there's a reason why they call it a weighted average, okay, and it's based on this principle that the heavier something is, okay, that their speed afterwards. If you collide a heavy thing with a light thing, both objects are going to travel in the same direction as where the heavy thing was going to begin with. If you collide a light thing with a heavy thing, the light thing will bounce off, okay, and the heavy thing will move on. So, you follow that? Okay, the heavy thing will cause the light thing to take off. If it's light and hits the heavy thing, it'll bounce back, giving a little bit of momentum. Okay, imparting some impulse upon the other object. So, we'll talk. Okay, so when 1 collides with 2, okay, we've talked about impulse, right? This is our impulse, right? Delta P is our impulse. Okay, so this has all the momentum right now. This has 0. When they collide, this is going to walk away with some momentum. 2 is going to have some momentum. Okay, here's the after. It's going to have V2 final going away. 1 is going to have V1 final going the other direction. All of a sudden, this 2, the second cart here, has momentum, right? Okay. Therefore, it has a change in momentum, and it has acquired an impulse to make it move. Yeah? That impulse is going to be equal to the amount of momentum that the other cart lost. Yeah? It's a conserved value. Okay. So this brings us to, and see, I'll just go this way with it. This brings us to elastic collisions. And to introduce you to elastic collisions, I need to move my board over to the side. And I'm going to show you something that you've seen before. Yes. This is obviously one of my best lessons in chemistry. And I'm going to use another one here in physics for really what it's used for. Okay. And I need to do this on a lighted stage, so to speak. So let me find a blank piece of paper here. That's that. Ah, I have no blank paper. I have blank paper. All right. Okay. These are a happy ball and a sad ball. All right. Okay. This one is happy. This one is sad. All right. Nice. Okay, there we go. So we have happy ball and sad ball. The happy ball has been very well adjusted since birth, since it was just a little oil droplet, and taken care of and fed well, and it has a bouncy, bubbly personality, and is a very okay. And so happy ball, when we play with happy ball, it likes to play with others, and so it bounces around. Okay, sad ball has been kept under a closet, just like Harry Potter, for the last 12 years of his life, and is allowed out once on Christmas to pick up its present, which is a lump of coal, and then returned under the stairs and fed through the feeding slot underneath, because it's a worthless piece of rubber, and it's really displeased us since it was it can't do anything right, and so it doesn't play very well with others, and it exhibits that in its behavior. Okay, you're angry with you, and so when the collisions it makes, and that's it, and that's sad ball. Okay, now what's actually happening is their sad ball here it bounces almost perfectly inelastically. Okay, meaning that all of the kinetic energy. So here it has potential, and it's close to the camera. Okay, and so potential energy here. I drop it, kinetic energy the instant before it hits the ground, and if it lands square and it doesn't roll any of it, all of its kinetic energy dissipates into internal heat of the ball. It goes away. It loses all of its kinetic energy. When that happens, when all the kinetic energy that it has before the collision goes away, goes into something else, that is an inelastic collision. The vast majority of collisions in our universe are inelastic. This, by the way, is a partially, so you guys could see that, it was bouncing. All right, happy ball experiences a mostly elastic collision. Okay, it retains a fair amount of its energy, of the potential energy, and keeps bouncing. However, it does eventually go away, because this is real life. Okay, and real objects tend to have inelastic collisions, okay, or relatively inelastic collisions, even if they do bounce. Now, we are talking about today. We're talking about perfectly elastic collisions for this, because I need to give you the the start for this before we start talking of our inelastics. So here are elastic collisions, and we have two conditions for an elastic collision. The first is always, because this is always true, that our initial momentum equals our final momentum. Okay. But the other one is that our total energy before equals our total energy after. Our total mechanical energy before is equal to our total mechanical energy afterwards. Okay. However, if we're talking about our carts down here, then we don't have any change in have any change in gravitational potential energy, and the change in our spring potential energy is internal to the system, right? Okay, the spring is within the system, so there's no change in mechanical energy. So really, what happens here is this is K initial and K final. That our initial kinetic energy equals our final kinetic energy. So here's the trick. We know, and we can find an equation for this. We just established an equation for the initial momentum of the system equals final momentum of the system. And we can pretty much come up with our kinetic energy one. That would be, 1 FMV squared on the left, 1 FMV squared on the right for each term. These suck. I will tell you right now, I hate these problems. They are awful. To actually solve them, it takes about 20 to 25 minutes of algebra to solve one of these problems. Go. No, I'm kidding. They're horrible, which is why. Okay, so here's why they're horrible. Okay, here's the catch. Check this out. This is M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That's not so bad. But we have two equations and two unknowns, assuming our masses are constant. 1/2 M1 V1 squared initial plus 1/2 M2 V2 squared initial is going to equal 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. This is a pain in the rear to try and solve. It takes forever. So, luckily it's done for you. In your book, on page 262, on page 262 in your book, the solutions for these are given to you. Okay, you will need to use them to solve a couple of your problems in your homework. However, keep this in mind. I have never seen this on the AP Physics C test for as long as I have been paying attention to the test, which is about 25 years.
So don't pay attention.
Okay, no. Know how to do it, but you don't need to be prepared to derive the solution to this for your AP test. Okay? You do not have to have that solution memorized. However, you need to understand the concepts of it. Okay. Now, then we have inelastic collisions. Okay, our inelastic collisions give us the same thing. Pi equals Pf. However, our initial kinetic energy is greater than our final kinetic energy because somewhere along the line we lose some of our energy in the collision to internal heat, to friction, to something, to a crumple zone in a car. All right, that is where we get our inelastic collisions. These are infinitely easier to solve, and as long as you hold on to and you grasp firmly to the idea that momentum is always conserved, always under all.